Right, any questions? Okay, so in the last class, we were discussing transformations of convex sets, and in an attempt to understand what kinds of inequalities we can handle in our convex optimization problems. Right, so firstly, we saw that if you take two convex sets, then, or in fact, any number of convex sets, then the intersection of those is also a convex set. So in other words, as long as you have inequalities which describe a convex set, combining multiple inequalities still results in a constrained set which is convex, right? Another transformation that we saw was that if I give you two convex sets, then the Minkowski sum, that is the set obtained by adding pairs of points, one taken from one of the sets and the other from the other set, also results in a convex set. Right? So if you have A1 and A2 which are convex, then A1 plus A2 is also convex. And in fact, this holds not just for the sum of two sets. You can take the linear combination of two sets, and that also results in a convex set. Right? So in fact, the Cartesian product of convex sets is also convex, and any affine transformation of a convex set is also convex. Right? And combining sort of 3 and 4, if you take multiple convex sets, then any affine transformations of these also results in a convex set. Okay. So the sort of inequalities that we've seen so far in our constraints have been the sort where, or at least the constraints that we have seen were expressed in the form of inequalities, right? So you have, let's say, f1 of x less than or equal to a1, f2 of x less than or equal to a2, f3 of x less than or equal to a3, and so on. But in fact, we can define more general versions of inequalities beyond just sort of component-wise inequalities, and we'll see how to do that in just a few minutes. Right. So in that regard, I define this notion of a proper cone. So it's a cone which is closed, it's convex, it is solid and pointed. Right. So you've seen closed and convex cones before. It is solid, which implies that it has a non-empty interior. It means that you can take an n-dimensional Euclidean ball. There exists some n-dimensional Euclidean ball which is completely contained inside the cone K. That is what it means to have a non-empty interior. Right? It doesn't matter what the radius of this ball is, as long as you can find a ball of non-zero radius, n-dimensional ball of non-zero radius, which is fully contained in K, this has a non-empty interior. So it's a solid cone. All right. So in particular, if I take, let's say, a two-dimensional plane in R3, then this is not solid, because there is no three-dimensional ball of any positive radius which you can fully contain inside a plane. Correct? So that's what it means to be solid. Also, we want it to be pointed in the sense that if you have a non-zero point x in the cone, then the negative minus x does not reside inside the cone. So in fact, if you try to visualize it in, let's say, 2 or 3 dimensions, then you can see that the cone is indeed, the term itself implies what we want. So it essentially is pointed, right? So it looks like a cone, right? The standard notion of cone. All right. So, but in fact, if you look at a general cone, then it need not be pointed. For example, if you take any straight line passing through the origin, right? That is a cone, but it's not pointed. All right. So, any questions about what is a proper cone? All right, so that was the definition, and we saw that one of the simplest examples of a solid cone is basically the non-negative orthogonal. right? So it's a set of all x for which xi is greater than or equal to 0 for all I. Right? So in 2 dimensions, it just corresponds to the positive or the non-negative quadrant. In 3 dimensions, it's basically the set of all points for which all the components are non-negative. Right? So that's the non-negative object. Another example of a proper cone is the set of all positive semi-definite matrices, but now not viewed. So recall that the set of all matrices forms a subspace of what dimension? The set of all matrices, n square, right? It's a vector space of dimension n square. But on the other hand, the set of all positive semi-definite matrices, this is the vector space in itself. And what is the dimension of this? Right, so it's n into n plus 1 by 2. Right, so when viewed as a subset of the set of all symmetric matrices, the set of all positive so that was the set of all symmetric matrices. The set of all positive semi-definite matrices lies within the set of all n by n symmetric matrices. And this set forms, so firstly, we've seen that the set of all positive semi-definite matrices is a cone. If you take any positive semi-definite matrix and scale it up by any non-negative number, then the resulting quantity is also a positive semi-definite matrix. Right? So if you have A, which is positive semi-definite, then alpha times A is also positive semi-definite. All right, and can you recall why this is true? Yeah. Okay, that's one way to put it. If you take the matrix A, it has non-negative eigenvalues. What would be the eigenvalues of alpha times A? It would just be alpha times the eigenvalues of A. And alpha is non-negative and the eigenvalues of A are non-negative. So the eigenvalues of alpha times A should also all be non-negative. Right? That's a straightforward way to show this. Okay. What else do we need to prove? To prove that this is a convex cone, we want to show that, well, firstly it has to, to show that it's a proper cone, we want to show that A is, of course, a cone. The set of all positive semi-definite matrices should also be convex. Right? And why is that true? So recall the set of all positive semi-definite matrices is denoted S plus superscript n. Right? We want to show that alpha A1 plus 1 minus alpha A2 is also positive semi-definite. Yeah, so we just take X transpose alpha A1 plus 1 minus alpha A2 for any vector X this is simply alpha times X transpose A1X plus 1 minus alpha times X transpose A2X. It's true for any alpha greater than or equal to 0, but in particular, I can take alpha between 0 and I've already shown that it's a cone, so that's fine. Well, in fact, for this I'm assuming that alpha is between 0 and 1. I can't take alpha to be any positive number. because 1 minus alpha could then be, if alpha is greater than 1, then 1 minus alpha would be negative. Right? But what can we say about this quantity? Greater than or equal to 0. So A1 is positive semi-definite. So X transpose A1X is greater than or equal to 0. And A2 is also positive semi-definite. So X transpose A2X is greater than or equal to 0. So this quantity is greater than or equal to 0. Right? So it's convex. Right? So now what about pointedness? If I take any matrix A, which is positive semi-definite, and A is not equal to 0, not equal to the all zeros matrix, then what can you say about minus A? So the eigenvalues of A are all greater than or equal to 0, and at least one of the eigenvalues is strictly positive, right? Because otherwise that would result in just the all zeros matrix. So if I look at minus A, then at least one of the eigenvalues is strictly negative. So minus A is not in S plus. All right. There are two other points that we have to show. One is that it should be solid, right? That's the main point that we need to show. So firstly, what do we need to show? We need to show that there is at least one ball of non-zero radius which lies inside the set of all positive semi-definite. Or in other words, even if we can understand what is the interior of the set of all positive semi-definite matrices, that would be good, right? But even before that, let's take a step further back and try to understand what is a ball in this case, right? So remember that the space that we're dealing with is the set of all symmetric matrices. Right? So in Rn, we know what a ball is. So in Rn, the ball is basically the set of all x in Rn such that norm, the 2 norm, let's say square, is less than or equal to r square. But now we're dealing with matrices, and not just the set of all matrices, we're looking at the set of all n by n symmetric matrices. Yeah? X transpose AX. So again, there are different ways to define the norm of a matrix. So let's use the standard Frobenius norm, which is basically the sum of the squares of all the entries, right? That's the norm square. So the norm of a matrix is equal to I comma j square root of the sum of the squares of all n. Right. So for Sn, what is a norm ball? Is it the same as, would it sort of have the same shape in some sense as the Euclidean ball? So let's take 2 by 2 symmetric matrices. Consider, so what is a 2 by 2 symmetric matrix look? A11, A12, A22, A12. So what is norm A equal to, or norm square equal to? Yeah? Yes. What? Correct. It's equal to the trace of A into A transpose. But, well, you could think of this A, right? So there are 3 free variables over here. So in some sense, you could associate it with R3. Correct? So right, so you could associate it with R3. But in R3, what would be the norm of the, so if you looked at the vector A11, A12, A22, right? These are the 3 free variables. So I could view this as a point in R3. Yeah, so that's a sphere. But if you look at the Frobenius norm of A, yeah, so it's going to look like an ellipsoid. So what is this equal to? Now, what is norm A square equal to? It's equal to A11 square plus A22 square plus 2 times A12 square. So the norm ball is not actually the standard Euclidean ball. In some sense, this corresponds to an ellipsoid. Right? So great, that's fine.
We have construed Frobenius norm.
Which other norm would you like?
We could have a custom norm which does not take 2 as a factor, it just takes.
Correct. That's also a valid norm. True. And effectively doesn't matter, for at least to show that. So remember that our goal is to show that the interior is non-empty. It so happens that it doesn't matter. No matter what you do, you can still show that the interior is non-empty, irrespective of which norm you choose. Yeah. Okay. So let's assume that this is going to be our norm. Then how do we show that? So let's say that I want to find out what the interior is. Okay. What do we want to show? I claim that the interior is in fact the set of all positive definite matrices. So what is this equivalent to saying? It means that if I take any A, if I take any positive definite matrix, then I can always find a ball of non-zero radius around it, such that all points within that ball are still within this set. Right? So effectively what I want to show is that this set is open. That's what I want to show. Right? Okay, I'll perhaps prove a slightly weaker statement in the sense that I'll prove that the set of all positive positive definite matrices is open. So it lies inside the interior. And for my purposes, that's enough because it implies that the set of all positive semi-definite matrices has a non-empty interior. Sorry? Then I'm showing that the set of all positive definite matrices lies inside the interior. I also have to show that the interior is contained in this, so that they're equal. But fine, right now all I want to show is that the interior is non-empty. Right? So effectively what I want to show is that if I take A plus some A prime, where this A prime has small enough norm, A is positive definite, and A prime is symmetric. So for every A,
That always
which,
not sure.
so that's what a ball is, right? Yeah. Third line. Okay. What I want to show now is that I pick any positive definite matrix. Okay, fix any positive definite matrix of your choice. Then there's some epsilon greater than 0. Let me rewrite. So fix any positive semi-definite matrix, positive definite matrix. Okay. What I want to show is that there's some epsilon, doesn't matter what it is, which could potentially depend on A, such that A plus A prime, where A prime is a symmetric matrix. This matrix is also positive definite as long as the norm of A prime is less than epsilon. So first, let's look at A plus A prime. So you fix a particular A, think of it as a point in R3, right? In the set of all symmetric matrices. Let's look at the set of all a plus a prime, where a prime has norm less than epsilon. What does it constitute? So again, think of these as points in some space. Doesn't matter what that space is. You pick a particular point A. You're looking at the set of all points a plus a prime, where a prime has norm less than or equal to epsilon. What is that? What is that set? Yeah? It is? Why line?
Because I'm fixing my point.
Yes.
Going towards one direction, which is given by this.
I don't care about what the direction is. I'm looking at the set of all a plus a prime, and the only constraint I'm placing on a prime is that the norm is less than epsilon. It's a ball, right? It's a norm ball. It's a ball of radius epsilon with center as a. Right? And I'm claiming that any point within this ball is also in the set of all positive definite matrices. Right? So basically, I'm picking a point A. Now, this is not in Euclidean space. You could think of it as Euclidean space, but now the metric is different. And I'm looking at a ball of radius epsilon around A. So the set of all positive definite matrices is going to be some weird set. In it's hard to visualize this particular set. But all that I'm claiming is that as long as A is positive definite, then there is still some more room. I can move around the point. There is some space around it, and it still lies in the set of all positive definite matrices. Right? And why is that true? Yeah? Okay, but that's what I want to show, that it lies inside. So if I take any two matrices, right, with some maximum eigenvalue and minimum eigenvalue, what can you say about the eigenvalues of the sum? That's not always true. You can't say that the sum of the eigenvalues is equal to the eigenvalue of the sum is not necessarily equal to the sum of the eigenvalues.
Maximum would be less than the sum.
The other way around. So if you have any matrices A and A prime, then the sum of the maximum eigenvalues is always going to be greater than or equal to the maximum eigenvalue of the sum. This is straightforward, but it's also true that the minimum eigenvalue of the sum of two matrices is always greater than or equal to the sum of the minimum eigenvalues of A and A prime. Okay, suppose that this is true. How does that help us? Correct. So as long as suppose that the minimum eigenvalue of A prime is larger than the minimum eigenvalue of, or as long as the minimum eigenvalue of A prime is larger than, strictly larger than, the negative of the minimum eigenvalue of A, what can you say about A plus A prime?
Length of the major and minor axis of the electron.
Okay, that's again, it's true only for positive semi-definite, positive definite matrices. You can't say that's true for general symmetric matrices. So if lambda min of A prime is greater than the negative of lambda min of A, what can you say about A plus A prime? What will be the minimum eigenvalue of A plus A prime? It's strictly positive. Right? So A plus A prime is positive definite. So similarly, you can also show that. So again, what does this imply? It means that the set of all positive definite matrices is an open set, right? And in fact, it's an open set plus the set of all positive semi-definite matrices has a non-empty integer, right? Now you can also show that the set of all positive semi-definite matrices is closed, but maybe let me just skip that particular proof. It's similar, it's technical, but let's see what this gives us, right? So why am I even defining proper codes? Right? I'm mainly defining this new abstraction because I can define what is called a generalized inequality. And these generalized inequalities behave in a sense very similar to the standard inequalities that we are used to. Right? So I'll say that, so given so take any proper cone. Okay. I'll say that a point X is less than or equal to, with respect to the cone K. So X is less than or equal to Y with respect to the cone K if Y minus X lies in the cone. That's my generalization of the standard inequality. So pick any cone you want, any proper cone you want. I'd say that I'm defining this new inequality, whatever it is. So I'll say that a point X is less than or equal to a point Y if Y minus X is in K. So for example, let's take K to be the non-negative ortho. So again, so K is a point in Rn. And what is a non-negative orthent equal to? Orthent. So it is the set of all points is the set of all points X in Rn such that all the components are non-negative. So in this case, what does it mean for X to be less than or equal to Y?
It implies x less equals to y.
Which?
X less equals to y.
Yes.
Y minus x belongs to.
Correct.
Then y minus x belongs to a implies x less equals to y, right?
Correct.
How do you write x less equals to y implying y?
No. So it's a definition, right? So it's two ways. Okay. So I should say if and only if y minus x is in K. Not saying that. So potentially y could be equal to x. Fine. So what does this essentially correspond to? So it's basically element wise greater than or equal to this, right? So it means that yi minus xi is greater than or equal to 0 for all I, or yi is greater than or equal to xi for all I. So if I choose to take x to be the non-negative orthent, then this generalized inequality is the same as saying, well, a component wise y minus x, component wise y should be greater than or equal to x. Right? But that doesn't necessarily, okay, but there's no reason that I could have chosen only the non-negative orthent. I could have chosen any other cone, any other proper cone for that matter. Right? So for example, if I take K to be, let's say in R2, the following cone. And how is this cone defined? The cone K is the set of all x comma y such that, let's say, x is greater than or equal to 0 and y is less than or equal to x. So in this case, what does the generalized, so what is really the generalized inequality? If I take a point x1, y1, then I'm saying that this is less than or equal to x2, y2. Effectively, what I'm saying is that so x2, x2 minus x1, y2 minus y1 should lie inside the cone, or x2 should be greater than or equal to x1 and y2 minus y1 should be less than or equal to x2 minus.
Basically, you mean that this center coordinate.
Yeah,
One vertex is all points are the same. Initially,
correct.
all the points are included at the same one.
Correct. So
Ultimately, it is coming out that x less equal to y with x. These are always x is equal to y component. Both the things.
sorry, can you repeat?
X is equal to y.
Mhm.
That implies x is equal to y component.
If I take k to be the non-negative author,
Both the
in these two cases, that may happen.
what's so special about this?
What is special about these inequalities? So, okay, so let me look at something a little bit different, okay? A slightly different example. Let's look at R2. And suppose my cone is now the second quadrant. Okay. For example's sake, I'll take k to be the second quadrant. Then what does it mean for x1, y1 to be less than or equal to x2, y2? Right. So again, how do you define the cone itself? So it is the set of all x comma y such that x is greater than or equal to 0 and y is, sorry, x is less than or equal to 0 and y is greater than or equal to 0. So by definition, x1, y1 is less than or equal to x2, y2 if x2 minus x1, y2 minus y1 is in the cone K, and that means x2 minus x1 is less than or equal to 0 and y2 minus y1 is greater than or equal to 0, which is the same as saying that x2 is less than or equal to x1 and y2 is greater than or equal to y1. Right. So again, I still have some component wise inequalities. I have not changed anything significantly over here, but these inequalities could be different from the standard inequalities that we're used to. Of course, the inequality, the way I've defined this, it doesn't seem to be particularly helpful, because these examples, fine, I'm still having some inequalities. I've not defined any new kinds of constraints other than component-wise inequalities. But things become a little more interesting when I say that when I look at the positive semi-definite form. So I say that A is less than or equal to B if B minus A is positive semi-definite. right? This is something you can't express just as component-wise inequalities. Yeah?
A and B is DHT, right?
A and B could be any matrices. I'm not saying that they should be positive semi-definite.
But A is in SN plus.
K is Sn plus. Sorry. Positive semi-definite.
You are seeing this in terms of the inner products, right? These are quantity.
In what sense?
X transpose B, X.
Yes.
So derivative X transpose
X. For all A. For all X. Right? So I have just one inequality over here. Right? But in fact, what it essentially corresponds to is saying that X transpose Bx is greater than or equal to X transpose Ax for all X in Rn. That's not one inequality or two inequality or a finite number of inequalities, right? It's an infinite number of inequalities. Which?
Bx, X, inner product Bx, X. Derivative inner product Ax.
Sorry, what are you trying to say? Okay. Fine, but again, it's not for one X, right? It should hold for all X. Correct? So you can't represent that using a finite number of component-wise inequalities. So these generalized inequalities that we define using proper cones still define convex sets and in many ways behave similar to the standard component-wise inequalities that we're used to. But it's different from the inequalities that we have over the reals, the standard inequality that we define over the reals. Right? So firstly, what properties does this have? If I know that X is less than or equal to Y, can I say that this is true for all Z? Assuming that this is an array. Right? So once again, the point that I want to emphasize is that when I'm defining this inequality, X and Y need not belong to the cone K. Right? They belong to the ambient space. If K is a proper cone in Rn, then X and Y could be arbitrary points in Rn. All right. So if you have a standard inequality, X less than or equal to Y and Y is less than or equal to X, then can you compare X and Z? But why is this true?
Element wise.
It need not be element wise, right? This could be any cone. It could be any proper cone, not necessarily. If I have the non-negative ortho, then I have element wise inequality. But I want to prove this in general. Yeah. Yeah. So since it's a convex cone, if I have two vectors in the cone, then the sum of those two vectors is basically a conic combination of those two vectors, which is also in the cone. Right? That's where we use the property that it's a convex cone. So in particular, this implies that if B minus A is a positive semi-definite matrix and C minus B is a positive semi-definite matrix, then C minus A is also a positive semi-definite. If I have X less than or equal to Y, then what can you say about alpha X and alpha Y? Again, why is this true? It's a cone, right? Because Y minus X is in the cone implies alpha times Y minus X is also in the cone. Well, can you say that X is less than or equal to X? Is it reflexive?
Yes.
Why is that?
0 belongs.
Exactly. It's a pointed cone and 0 belongs to the cone. Now, if X is less than or equal to Y and Y is less than or equal to X,
It's equal to y.
X equal to Y, and why is that?
Because the negative can't belong to y.
Yes. So that's because Y minus X is in the cone and X minus Y, which is equal to the negative of Y minus X, is also in the cone. But since it's a pointed cone, this implies that Y equal to X. So I can't define this generalized inequality using a cone which is not proper and still have the same properties that I had for component-wise inequalities. Well, yeah, so I'll get to that in the very next point.
We'll go towards the second one.
The second, yes.
I can't we use since A is a convex cone.
Uh-huh.
We are taking y minus x plus z minus y. I can't we take with some arbitrary alpha 1, alpha 2?
Why do you need to?
Also, body combination is alpha 1
Correct.
x plus alpha 2 y.
It's fine. Yes.
Why can't we take with some function?
Again, what is the advantage? Because what do I want to show? I want to show that z minus x is in the cone, right? That's my objective. And how can I generate z minus x from y minus x and z minus y? Just the sum. In fact, it's true that any conic combination of y minus x and z minus y is in the cone, but I don't need that. Right now, I only need this specific conic combination. So in fact, the inequality is also preserved under limits. So if I have x1, x2, x3, x4, and so on, if I have a sequence of xn's and I have a sequence of yn's, such that component-wise each xi is less than or equal to yi, then it so happens that the limit as n tends to infinity, xn is less than or equal to the limit as n tends to infinity of y. So something like this does not hold if K is not closed, right? So for example, it's not exactly the same, but suppose I have a sequence xn which is strictly less than yn for all n. Does it mean that the limit n tends to infinity xn is strictly less than the limit n tends to infinity yn? If I have two sequences such that each element of one sequence, the ith element of one sequence is strictly less than the ith element of the second sequence, does it imply that the limits, the first limit is strictly less than the second limit? The limit need not exist, but suppose that the limit exists. Yeah? How many say yes? This has to happen. How many say no? Other people? Okay, can you give an example where this is not good? Yeah. So for example, I can take xn to be 1 by n, yn to be 2 by n. So clearly xn is strictly less than yn for all n. But what is the limit as n tends to infinity of xn? 0. The limit as yn as n tends to infinity is also 0. That equal.
What if we introduce the equality?
If you introduce,
What if we make it less than or equal to less than?
then it's true. Then this is true. As long as the limits exist. All right. So once again, why is all of this helpful? Right? How does it help in solving problems at all? I've defined a new set of constraints, and the point is that I can now expand the class of constraints that I can handle. It's not just component-wise inequalities. If I have a problem which has component-wise inequalities, then I knew how to handle them. Right? But now it doesn't necessarily have to be just component-wise inequalities. I can also handle inequalities, constraints of the type some matrix should be a positive semi-definite matrix and beyond. Correct? So let's see one particular example. All right. So have you seen positive semi-definite matrices? Any application where you've seen positive semi-definite matrices before? Yeah?
PCA.
Okay, PCA. Let's go down to something even more elementary.
Okay. It's not really.
Okay, where did you see it?
It's equal to be solution to exist. Or it also the goal.
Well, okay. Okay, let me focus on something else. Have you seen a positive semi-definite matrices in, fine, A transpose A is positive semi-definite, that's true. In probability, have you seen positive semi-definite? The covariance or the correlation matrix is positive semi-definite. So what is the correlation matrix equal to? So if I have a random vector, or you could have multiple random variables and you just stack them up to form a random vector, then the expectation of x transpose is what I call the covariance, the correlation matrix. Right? Or if you want to look at just two random variables, then what is the correlation matrix equal to? Just expectation x square, expectation xy, expectation yx, which is the same as expectation xy, expectation y square. So for any two random variables x and y, you can define this correlation matrix where x square, expectation x square and expectation y square are simply the second moments of the random variables x and y. Expectation xy is just the correlation between the two. Right? And sometimes if you look at a sequence, then expectation x transpose consists of both the terms, the autocorrelation terms and the cross correlation terms. Whatever, that's not particularly important, but fine. This is how you define the correlation matrix. Obviously it's symmetric. Why is it positive semi-definite? The eigenvalues are in how? Try to think of something even simpler, right? Just go by the definition. What is the definition of the correlation matrix? It's expectation x transpose, right? For this to be, let me call this Cx. Okay. If Cx is positive semi-definite, then what should happen? Yeah. So if I take any vector, let's say u, then u transpose Cx, u should be greater than or equal to 0 for all vectors u. But what is this equal to? This is u transpose expectation of x transpose times u. U is deterministic, correct? So this is the same as expectation of, just by linearity of expectation, this is U transpose X, X transpose U. Which is what? So it's just expectation of U transpose X, the whole square.
So can we also say, so XX transpose is like always what do you say? PSC. So CX is essentially like a expectation is like taking a convex combination. So
Sure. Yeah. That's another way to look at it. Right. So this is a sort of more probabilistic way of showing that the correlation matrix is always positive semi-definite. Okay. Now suppose you are given a set of 3 random variables. You are making some measurements on the field, and you want to find out how correlated some of the values are. Okay, what is the maximum amount of correlation that you can have? So suppose you have 3 random variables, X, Y, and Z. You're trying to find the statistics of these random variables somehow using some kind of measurements, and you know that the correlation matrix is of the following form: 1, 1, 1. This is whatever rho xy, rho xz, rho yz. Right, so the correlation between x and y is rho xy, the correlation between x and z is rho xz, and correlation between y and z is rho yz. Just standard. All that the information that you know is that the second moments of x, y, and z are all equal to 1. Okay. Now maybe you make some measurements. You know that rho xy is between 0.2 and let's say 0.3. And maybe you know that x and z are positively correlated. And you want to know what is what can be the maximum amount of correlation between y and z. So this is basically an optimization problem where your objective function is rho yz. You are given 3 constraints. One, that rho xy is between 0.2 and 0.3, rho xz is greater than or equal to 0. And the third constraint is that this matrix should be positive semi-definite, because it's a correlation matrix. You know that this is a correlation. In fact, you can even just solve this directly using CVX pi. So my variable is now a 3 by 3 matrix. That's my correlation matrix. But it's not any 3 by 3 matrix. It's basically symmetric, right? So I can say equal to true. So this instantiates a 3 by 3 matrix as the variable which is symmetric. Okay, now what do we want? We want some constraints. Okay, and what are all the constraints in this case? C
0.
0 1. So it is, yeah, so rho xy is C01. It's between 0.2 and 0.3. Oh, sorry, minus 0.2 and 0.3. Less than or equal to 0.3. What else? Is greater than or equal to 0. Yes, we do have to. So C00 is 0 is 1. C11 is 1 and C22 is 2. That is 1. Okay, and it's positive semi-definite. You can say that by saying greater than 0. Okay, what next? Yep, so objective so C greater than 0 means C should be a positive semi-definite matrix.
That is the how.
That's how it works.
Okay.
Yes. So CP dot maximize 1 2. Next. Let's prop dot solve. Yeah. Happens to be close. This one. Sorry? Yeah, it's effectively 1. Right? So this was sort of a new type of inequality or new type of constraint that we have introduced now. and it is that C should be a positive semi-definite matrix. And this can be generalized. You can say that A should be greater than, or A minus B should be a positive semi-definite matrix, which is like saying A greater than B.
So what if we replace 0 by 1 then?
Greater than 1?
Does it have a big?
So I'm guessing this will take this to be the all ones matrix, or the, yeah, I'm guessing it will take the all ones matrix. Yeah, exactly. So it creates a generalized inequality.
What if C greater than?
In fact, we've been using generalized inequalities even before. When we say that whatever x greater than or equal to y, you're using component-wise inequality, which is still a generalized inequality. But that was defined with respect to one particular proper cone. But now we are using a different proper cone, which is the cone of positive semi-definite matrices.
How does it solve? Whatever all the possible solutions and then
No, that's impossible to do. So again, internally what CBXY does is it identifies what kind of a problem it is, whether it's let's say it's a linear program or a more general convex program and so on, and it invokes a solver. There are already solvers written out there, and there are different algorithms, most commonly what are called interior point methods. Again, we will not talk about interior point methods in this particular course, but for example, gradient descent is, it's not an interior point method, but it's a gradient based method, which is also one way of solving a convex optimization.
So does it let you solve for positive definite?
Sorry?
Does it let you solve for C is positive definite?
It won't. And why do you think you can't?
Data close.
Yeah, it's a closed set. So typically your constraints are taken to be closed convex. Because of course, if you take it to be open, then even a solution may not exist. Any questions? Okay, so maybe this is a good point to stop. But just some food for thought. If I define a generalized inequality, then can you compare every pair of points? Are every pair of points comparable? If I take any two numbers, I can either A is greater than or equal to B, or B is greater than or equal to A. One of those two has to hold. But if I take a generalized inequality, then does this property hold?
The finite.
it depends upon the cone. How do you describe generalized
Yeah,
inequality?
in general.
Is it a finite?
What do you find? Two points, right? So for example, in Rn,
Sir, what if we put the say greater than 0?